Okay, so now let's look at Newton's first law with torque. So what will it say? It basically say without an external net torque, can you guess what will happen if there's a system without an external net torque? The system will remain at rest, rotationally speaking, or rotating at a constant angular speed. Okay, so if basically it's Newton's first law says that if you the original Newton's first law says that if you have no net force, no external net force on a system, it will continue moving. If it was at rest, it stays at rest. If it was moving, it stays moving. Here it says if you don't have a net torque as well, then if it was at rest, it's at rest. So this pen is going to be staying at rest in space. Right now it's also falling. But you see that there's no net torque on it, so it's gonna not rotate, right, like this. But as soon as I introduce a force, which I just did, right, on the side like this, then that is away from its center of mass. Now it will start rotating. So yeah, so it says if it was at rest, it stays at rest. If it was rotating at first, it will stay rotating. So if you take an apple into space and give it a spin, it will just spin forever. It will not stop without air resistance, without nothing touching it. Newton basically, you know, it's a good question, right? If you say, hey, wouldn't it stop? The other one would ask you back, why would it? I mean, there's nothing touching it. So there's no force applied and no force, no torque applied to it. You know, it just keeps spinning, all right? So how do we apply this to anything? So let's see. So let's say I have a seesaw, right? A balance like this. Okay, so I have a fulcrum over here. So let's call it a pivot, right? From here, so this is the rotational axis. As you see, the system will rotate about here. Usually it's fairly easy to determine with your common sense looking at this, which way things will rotate. So this is on Earth, so there is going to be gravity, okay? So this is going to be like this, and I'm going to put two masses on here. So just to, it's a little bit, technically you can put only mass on top, but let's say I'm actually putting it on, yeah, on here, but we'll assume that the seesaw plank is thin enough that the mass is basically applying, like I'm attaching the mass on here. All right, so let's use our favorite numbers. We'll put a 2 kilogram mass over here and a 3 kilogram mass over here. And however, this guy is going to be 5 meters away from the pivot. This guy is going to be 10 meters away. Now, my question to you is, which way will it rotate? Okay, now you need to calculate the net torque on it. All right, so what we will see is, let's draw the free body diagram on this plank first, but this time we're not going to draw everything from the center of mass of the plank, nor the rotational axis, but we're actually going to draw where the plank, this plank over here is experiencing the force. So here it experiences a force on the plank from the 2 kilogram block. Here, it's a contact force on here, right? So here it is a contact force. It's experiencing a force on the plank from the 2 kilogram block, 3 kilogram block. Can you make a guess which way it will rotate? Okay, I don't know before we calculate, but if we calculate this, we might get some insight onto this, right? So yeah, let's see. So we'll need to calculate the torque. So what's the net torque on this object? So let's write down the vector. The net torque is the torque from the 2 kilogram on the plank plus the torque from the 3 kilogram block on the plank. What's the now let's choose let's choose, just like we need to choose an axis, sort of XY axis with normal linear motion. Here you want to choose a rotation direction. Okay, do you want to choose So let's just get an intuition first. For here, let's call it R2, the displacement vector to the 2 kilogram block and displacement vector to the 3 kilogram block, right? And just so I can write things easier, I'll call this F2 and F3 like this, okay? So promote these guys to vectors. Okay, so this guy is, the torque of this is R2 cross F2 plus the torque of on this is R3 cross F3, this, okay? Which one do you want to call positive and which one do you want to call negative? So depends, you see that this guy is rotating it. If I move it to here, you see R2 is pointing this way, R2 cross F2 is pointing into the board, but R3 cross F3, right? If you move things to compare the same point, R3 cross F3 is out of the board. So this will create a torque into the board, and this will create a torque out of the board. Okay, so let's call this axis, let's call it out of the board positive, whatever, you can make a choice, right? So call it out equals positive. Okay, so now we'll just look at, because both of these both of these vectors, I should say, both of these torque vectors lie along the in and out direction of the board. So so it's basically a one-dimension problem. I don't really need the full vector terminology, and I can just use the magnitude of this. So now, as you can see, from this step to this step is still a vector, but from here to here, they're going to take the magnitude, okay? So I'm going to choose out as positive. So this guy is going to R2 cross F2, it's going to be out. So it's going to be positive of R2 F2 sine theta. Let's say theta 2. So theta 2 is the angle between R2 and F2, and R3, I just need to move them to the same point to compare. So R3, and this is the angle, included angle, I'll call it theta 3. It's R3 F3 sine theta 3, right? But because this is perpendicular to each other like that, right? So this is going to be, both of them is 90 degrees, and sine of 90 degrees is 1. We're good with that. This guy is, I'm choosing out of the board as positive, so this guy is going to be positive. And I'm choosing, this guy is, sorry, this is negative, right? Because out of the board is positive, R2 cross F2 is negative. So I need to put, so R2 cross F2 is negative of this, right? Plus positive of R3 cross F3, okay? So the net torque in the, so let's plug in the numbers now. We are ready to plug in. So R2 is, the magnitude of R2 is 10. The force of R2, this is 2 kilograms. So this force over here is basically the weight of this guy. So I'll just use G equals to 10. Okay, so this is 2 mg. So this will basically equals the weight of 2, which is m2g, right? So let's say 20 plus R3 is 5, and F3 is the weight of this guy, which is 30. Okay, what's the answer? This is minus 200 plus 150. Aha, good. I get a negative number. Okay. All right. First of all, this is the magnitude. Do I need any directions over here? Yeah, it's negative, but outwards it's positive. That means the vector is actually, well, the magnitude is this, but the direction is actually into the page. Okay, so the magnitude is 50. So if you want, you can say the magnitude of tau is equals to 50, and then the units then direction is into the page. Okay. Now, what is the units over here? Okay. You might wonder why can a magnitude here be negative? It's because technically from this step to this step, I should be putting overall magnitude sign like this, but the direction kind of I can do it slightly more properly, to be honest, with the full vector sign. I'll fix that in a second, just to make it more more formal, so you won't get confused with that. But yeah, the magnitude is 50. What is the units? The units is newtons and meters. So the torque is 50 Newton meters. The direction is into the page. So which way is this rotating? If the direction is into the page, it's telling you it's rotating this way. So the 2 kilogram actually win because this guy is actually further away. Okay, so it's going to rotate this way. And if I know, so we'll talk about how fast it will start rotating if I let go of the system. All right. So how does so now I can change the question a little bit and ask, what distance should this be if I don't want it to rotate? Then that means the net torque should equal each other. Okay, so the torque from 2 should equals to this. So there's no net torque, then the system will stay still. Okay, so before I do that, let me fix the sign, the vector issue over here first. I know it's bugging someone. So I'll call the outwards positive K. So this is I'll use a different color. So slightly more formally. Outwards positive K hat. Okay, so this is the Z axis pointing out. Okay, so the net vector is, this is the magnitude times which one? So R2 cross this is going into the board. So it's the magnitude is R2 F2 sine theta 2. That's the magnitude times minus K hat plus R3 F3 sine 3. But this is out, right? So this is positive K hat. So the tau net vector is this. And we have this, right? So this is going to be 1, this is going to be 1. So this is 10, 20, and then the minus K hat is here. And here will be positive K hat. So I will have minus 200 K hat plus 150 K hat, right? And which means it's minus 15 Newton meters K hat. Okay, so the magnitude is 50 Newtons meters, and the direction is negative K hat. Okay, so you might say, what happens if I define going in as positive K hat, or even I hat or J hat? It's completely fine. It's up to you. So in the exam, make sure you write out what you are, which way you're calling positive and negative, because it will affect the answer. But if you describe it in word, in whether it's positive and negative depends on your choice. But whether it's the result is whether it's into the page or out of the page, everyone will agree on that. So that part will be the same. Okay. Yeah. So all right. Good. So now you see a little exposure of how the cross product is useful. And yeah, let's solve the question of if I have X over here, right, and I don't want it to rotate, how far? So this is a fair question, right? So if you put a 3 kilogram baby over here and you want to put a 2 kilogram baby on the other side, you want to know how far you want to put them, so the babies will just balance over there and not slide off the seesaw. All right. So in case anytime soon you need to balance babies, this is how you're going to calculate it, right? So I need the torque of 3. I needed to balance the torque of 2. All right, so this is one way to think about it, or you can say torque 3 plus torque 2 is equals to 0. All right, sorry, I should say so there's two ways to do it: the full vector way, or just balancing the magnitudes. Right. So yeah, I'll do the without the vector way first, balancing the magnitude. Okay, so the magnitude of torque 3 should be the same as the magnitude of torque 2. Okay, the magnitude of torque 3 is R3. Well, you need to understand, right? So this one is giving a torque that is sort of counterclockwise, right? R3 cross this, right? This guy's, and it's also intuitive. This guy's pushing this way, it's going to rotate the whole system this way. So out of the board way. If this guy's pushing this way, it's going to rotate the whole system into the board or clockwise, right? So if you don't want to rotate, the magnitude of the torque out of the board should better equal to the magnitude of the torque into the board. Okay, so yeah, so you have this, the magnitude of this better equals to the magnitude of this, but since we know that these are 90 degrees, so these would just be 1. Okay, so now we'll plug in the numbers of R3 is, what is our unknown? Our unknown is R2, right? So let's make that the subject. So notice no vectors everywhere. I'm just balancing the magnitude. And I have R3 times F3 divided by F2. Okay, and now I can plug in the numbers. R3 is placed 5 meters away from the fulcrum, from the pivot, and F3 is, what's the weight again? 30. And F2, the weight is 20. Okay, so this is 3 over 2 or 1.5, right? So this is 15 over 2 or 1.5 times of 5 is 7.5. What's the unit? Meters. Okay. Any directions? Well, yeah, to the right. But in terms of just x, right? So that's the magnitude of R2 here. I could have just called that R2. Then it's 7.5. So now you know that if you have 2 babies of this weight, you know where to put them. All right. Good. So this is the you can do it completely without vectors. But try to learn both as well, so you understand if it's not there's pros and cons for both ways. Is if you can do it without vectors, do it without vectors, right? No one wants to torture yourself, right? But if you find it hard to construct a problem, then if you do it with vectors, it's in some sense it's nicer. You can just shut off your brain and just and it will work, right? So you go like from Newton's first law for rotations, the net torque, I want it to be 0. Okay, so I want 0 to equals to the net torque is the torque from 2 and the torque plus the torque from 3 in vector. So if you do it in vectors way, then you can completely shut off your brain and don't worry about which one's positive and which one's negative. You always add vectors, right? So just like in the linear examples of force, if you use the vector version, it's always addition, right? But if you don't do the vector version, then you need to worry about if I have a force pushing just like this, right? If I have 5 newtons pushing this way, 2 newtons pushing this way, or let's say 20 newtons pushing this way, what's the net force? So now you need to worry about, oh, it's this one subtract this one, or this one subtract this one, so it's 15 newtons left, right? So now you need to think a little bit more. But if you do it the vector way, you just go, oh, that's F1, F2, right? So F1 is 5 in the positive I direction. Let's call that X or positive I, and plus F2 was 20 in the negative I direction, right? And then now you just do the math and you go like minus 15I, right? So how do I interpret that? The magnitude is 15, the direction is minus I. right? So this is the vector ways. So this is the rotational counterpart or analog to that. Okay, so R2 over here, it's the magnitude of tau2 times into the board, right? So I'm going to define out of the board, out equals to positive k. Let's try to do it other way around, right? So let's say someone is going to come and say, hey, I'm going to define into the board as positive k. Will it change my answer? Let's see. All right. So our torque 2 is this, right? So that's into the page. So it's plus k because it's into, and the magnitude of tau 3, but this is out of the page. So if into is plus, out of is minus. So what's the magnitude of this? Again, R2 F2 sine theta 2, but sine theta is 1. R2 is unknown. F2 is 20. That k hat. Yeah, we'll do that separately, one thing at a time. Tau 3 is over here, right? So R3 F3 sine theta 3, but minus k hat. So you're gonna do this. Okay, so now I have R2 and then R2 F2 minus R3 F3 because sine theta is going to be 1. What do I know? I know this, I know this, I know this, and I want to solve for this, right? So what does that mean? So this all have to equals to 0. So that means, right? Yeah, you can say basically that has to equals to this itself has to equal to 0. Or if you like, you can move. There's many ways to now do this, right? You can move this to the other side and say this. So you can move this to the other side and say that is 30, 5, 30, okay, equals to R2, 20, okay, right? So that's 20 R2 k hat equals to 150 k hat. So what is R2? So R2 must be 150 divided by 20, okay? So that's 15 divided by 2, that's 7.5 meters, okay? So, or you can just directly say, hey, that has to equals to 0 because this whole thing is equal to 0. So just like, you know, a plus b, a minus b equals to 0. What does that mean? That has, or times c equals to 0. So either c is 0 or a plus b is 0, right? So, but k hat is not 0. So this has to be 0, okay? Obviously, one is less work than the other. This is less steps than the other. But this one, you can really see where Newton's first law sort of come in. So there's pros and cons. And as you can see, basically on a more higher level, one, you just shut off your brain and just apply the laws of vectors. The other, you have to think through it a little bit more. So I'll leave it up to you. It's good to train both muscles and see, yeah, and be able to see both. Okay, so that's Newton's first law. And now we'll go and look at the second law.